Hi, folks. We turn now to general relativity. I'll probably do this in two shortish lectures so as not to fry too many neurons. Let's begin by discussing the sense in which general relativity is general. Special relativity is special because it concerns only inertial reference frames. It is concerned only with relative motion that is unaccelerated, that is constant velocity. General relativity concerns all reference frames, so there's no longer a restriction to inertial reference frames. The principle basically says that the laws of nature are the same in all reference frames, whether they are accelerating with respect to one another or not. The name of this principle is the principle of general covariance. It won't matter much since your final exam is going to be open book, open notes, but I'm not particularly interested in you memorizing the name of this formula. I am interested in you understanding what it means. That will not become clear until we've rolled up our sleeves and gotten into general relativity a little bit, but the slogan that should give you a sense of it anyway is that the laws of nature are the same in all reference frames. There is no longer a restriction to reference frames that are moving at constant velocity with respect to one another. This was a beast mathematically. That's why it took a mind like Einstein's the better part of 10 years to get there. He spent a lot of that time single-mindedly wrestling with Newtonian gravity. And in the wrap-up of our lecture on special relativity, we briefly discussed why. Let's do that in a little more detail now. Classic Newtonian gravity is incompatible with special relativity. Newton's gravitational force operates everywhere in the universe, but its strength depends on only two things. It is directly proportional to the mass of the bodies in question, and inversely proportional to the distance between them, notably the square of the distance between them. Those are the only magnitudes that figure in Newtonian gravity. So there's no variable for the time involved in the transmission of this force. So, to consider an example, according to Newton's theory, if the sun were to disappear, we should feel the effects of that disappearance immediately on the Earth's orbit. According to special relativity, it would take at least 8 minutes for us to become aware of this because no influence can be transmitted at faster than light speed. So, those of you who are sort of getting the narrative of the course are probably starting to see how some of this comes together. The mysteriousness of Newtonian gravity is now amplified because it's a kind of instantaneous action at a distance. And Einstein is wrestling with his theory of special relativity, which rules out as physically possible instantaneous action at a distance. So Einstein in 1905 to 1906, as he's finishing up special relativity, now faces a new dilemma. He has already, in 1905 to 6, reconciled the principle of Galilean relativity and the non-relativity of the speed of light in a vacuum. Now he's got a different reconciliation project. How do you reconcile Newtonian gravity with special relativity? He was able to come up with special relativity by dropping a hidden auxiliary hypothesis, namely that space and time are unaltered by motion. Here he can't pin the blame on an auxiliary hypothesis. He's got to modify Newton. Newtonian gravity is going to have to be changed almost to the point of unrecognizability. And again, that shouldn't surprise us as much as it would have had we not already encountered how mysterious Newtonian gravity is. Newton himself was puzzled by it. How can you have a pulling force that operates without contact? God seems to have set things up that way. Newton's defender Hume said, at the end of the day, all we could do is say this is the kind of thing that always happens. Einstein has to go somewhat metaphysical. And so Newton had effectively banned from physics the question, what is gravity? Einstein brings that question back to physics. He brings it back in terms of something kind of like Kepler's clockwork metaphor. He wants a mechanism by which gravity works. That's a tall order, and Einstein had to think about it for a long time. It's conceptually difficult, and it's mathematically bare. But for our purposes, there's a simple principle here that's doing the work. DeWitt calls it the equivalence principle. And it says that effects due to gravity and effects due to acceleration are indistinguishable from one another. Basically, general relativity amounts to the equivalence principle. I'll talk more about that in just a moment, and the above-mentioned principle of general covariance. The equivalence principle is going to allow you to see why and how the laws of nature are the same in all reference frames, whether they're accelerating with respect to another or not. So let me try to set the table for this maybe a little more than DeWitt does. Special relativity shows us that time is as accurate measurements of time are. Space is as accurate measurements of space are. We couldn't reconcile the principle of the constant velocity of light and Galilean relativity because we kept thinking that space and time would have to be altered by motion to reconcile those. Well, it turns out they are altered by motion. So now Einstein's going to get a generalization of special relativity by taking the same kind of approach to gravity. Gravity is as gravity does. What do we measure gravity to do? And that's what we measure gravity to be. Well, what does gravity do? It's an accelerator. It accelerates things. So we're going to get a grip on the mysterious thing, gravity, by getting a handle on the less mysterious thing, acceleration. Let's compare this to the principle of Galilean relativity. Galileo's metaphor was something like a ship. If you're in a sealed, windowless compartment on a ship that's moving at constant velocity, you can't tell how fast you're going or whether you're at rest with respect to a given reference frame. There's no experiment you can perform that will give you any indication of, scare quotes here, real motion. You will, however, feel acceleration. If somebody throws an anchor off the side of the ship and it suddenly catches, then you will be thrown as the ship comes to a sudden stop, right? What Einstein realizes is you can feel acceleration. What you can't feel is the source of the acceleration. There is no detectable difference between the way gravity pulls you down and the way that an upward acceleration pushes you down. It's weird that we call one a pull and the other a push. So instead of Galileo's sealed compartment in a ship, we're to imagine a sealed container the size of an elevator. No windows, no way to see what's outside you. You have no way to tell the difference between being in a gravitational field that pulls you down versus being accelerated upwards. And you know what an elevator does, right? It presses your feet into the ground. It will make things fall, just as a gravitational field does. So it's the equivalence between a gravitational field and an acceleration that is the heart of general relativity. How do we put these things together? This is how the equivalence principle is going to explain and support the principle of general covariance. Any observer can think of herself as stationary even if she's accelerating. She will feel accelerations, right? Accelerations are felt, not necessarily with respect to absolute space, as Newton thought, but acceleration of any sort has discernible effects. It tosses us around. If she is accelerating, she can still treat herself as stationary. What does she do? She posits a gravitational field that would allow her to think of herself as stationary while undergoing those accelerations. It's the equivalence of acceleration and gravity that allows any observer to think of herself as stationary. So just to be perfectly clear, with special relativity, any observer who is in an inertial reference frame, who is not accelerating, is entitled to think of herself as stationary. With general relativity, any observer is entitled to think of herself as stationary. She just has to posit a compensatory gravitational field. So the comparative mystery of gravity is now basically being reduced to or identified with the comparatively straightforward notion of accelerated motion. The math gets a little hairy here. You have to plug in the measurement aspects of special relativity to acceleration. right? As I accelerate with respect to you, my speed with respect to you increases, so my rulers will gradually get increasingly smaller and my clock's increasingly slower. You will be glad to know you are not responsible for any of this math. Let me just close this first half of the lecture by previewing what comes next. Gravity, as we've seen, is as gravity does, and acceleration is what gravity does. But acceleration is a change in motion. So gravity, like acceleration, alters the measurement of space and time. And since there's nothing more to space and time than space and time as they are accurately measured, gravity, like motion, warps space and time. We'll see how that part goes in the second half of this lecture on general relativity, which I'm trying to